Okay, so in one of the examples that we discussed above, what we obtained was the following. We said that for the Lagrangian, a half y dashed squared minus a half y squared. One of the Noether symmetries we obtained was, and I won't label it, I'll just go that this was cos x d by dy with the corresponding gauge term given by f equal to minus y sine x. In this case then, if you were to use Noether's theorem, then by Noether's theorem, a first integral would be I equal to L times xi. Xi in this case is 0 plus eta, which is cosine x, minus y dashed times xi multiplied by dl dy dashed, and if you do the derivative of L partially with respect to y dashed, you notice that's very straightforward, y dashed minus the function, the gauge term, which is minus y sine x. If we simplify that, we get very simply, this is then y dashed cosine x plus y sine x. If we do a check on this, right, then the total derivative of I with respect to x should give us the equation y double dash plus y, which is the left hand side of the equation, times some factor. So let's do this total derivative of that function I. If you differentiate y dashed, you get y double dashed times cos x, and then if you leave the y dash as it is, you differentiate cos x, you get minus y sine x. If you differentiate y sine x, you get plus y dash, derivative of y is y dashed, if you differentiate totally, y plus y times cos x. And that, you see, gives us the y dash sine x cancels off. We get cosine x into y double dashed plus y. Now if you recall that this was a Lagrangian for the differential equation, or leading to the differential equation, y double dash plus y equal to 0. And that y double dash plus y features on the left hand side, or features from the left hand side. So the thing that I've squared out there is then equal to 0. So this is equal to 0 on the differential equation. So this is then cosine x times 0, where that 0 comes from there, from the differential equation, which is equal to 0. So indeed, this function I constructed via Noether's theorem using the Noether symmetry, there and the gauge term there, gives us that as the first integral, and you would get 5 different independent first integrals if you were to use the 5 different Noether symmetries. The important thing to keep in mind is, as I mentioned previously, is this factor here. It turns out always that if you were to check the total derivative of I with respect to x, you always get the left hand side of the equation if the equation is equal to 0. So this will be the left hand side of your equation, the differential equation, and this factor is always eta minus y dashed xi, where eta and xi come from the Noether symmetry xi d by dx plus eta d by dy. This factor is sometimes referred to as a multiplier, and if you continue with your studies on constructing conservation laws for general classes of partial or ordinary differential equations, these multipliers feature prominently. And this, of course, you will see even in the proof of Noether's theorem, that di dx equals eta minus y dashed xi multiplied by the curly E on L, where curly E on L is your Euler-Lagrange equation, and that equals 0. So that is one aspect of, or at least one application of Noether's theorem. Now, having looked at this, let's just look at that y, the function I constructed here, which is y dash cos x plus y sine x. What I want to do is to see the relationship between the Noether symmetry x that was used to construct the I and the I itself. So what I want to do now is to see the relationship between this Noether symmetry and this conservation law I, which was constructed from that Noether symmetry. Right, so we're going to do the function, the Noether symmetry, the vector field x operating on I. So let's just rewrite, let's just rewrite the Noether symmetry. The Noether symmetry here was cosine x d by dy, and it led to the first integral y dashed cos x plus y sine x. So it's y dashed cos x plus y sine x. And in order to see the relationship between this x and this first integral I, we're going to check whether the function I is invariant under this vector field x, its corresponding vector field x. To do that, we take the vector field and operate on I. If x on I is equal to 0, I is invariant under x. If x on I is not equal to 0, I is not invariant under x. Right, but to operate x on I, because I contains first derivatives, we need to prolong x to x1, up to first derivatives. So xi is 0, eta is cos x d dy, plus we need to find eta 1 to get this thing there. Eta 1, remember, is always the total derivative of eta with respect to x minus y dash the total derivative of xi with respect to x, which in this case is, since eta is 0, if you differentiate eta totally with respect to x, eta is just cos x, so this is then just minus sine x. So this term here then is minus the sine of x. That is x1. So that, therefore, x1 on I is equal to, the vector field is then cosine x d by dy minus sine x d by dy dashed operating on the function I. This is equal to cosine x, the partial derivative of I with respect to y. That means y is your variable, everything else is constant. If you differentiate the function I, here's the function I, you differentiate it partially with respect to y, the derivative on the first term is 0, the derivative on that term with respect to y is 1 times sine x, so it's sine x. Then it's minus sine x multiplied by the derivative, that's y dash, the derivative of I with respect to y dash. If you differentiate the function I with respect to y dash from this term here you get it is 1 times cos x. And then that's equal to 0. Right? So i.e., let me just repeat that. What you get is x1, the prolongation of x at once, operating on I is equal to 0. So that, therefore, this function I, the first integral constructed from the Noether symmetry x, is in fact invariant. Is invariant under the vector field x. In fact, it is a theorem that says that if a first integral is constructed from a Noether symmetry, xa, and this would normally be via Noether's theorem, then x on I is equal to 0, then I is an invariant function, of the very vector field that led to the construction of I. This has all kinds of consequences on the reduction of differential equations. I'm not going to get into the details, but we did mention in the chapter where we found Lie symmetries of differential equations, we said that every vector field, a Lie symmetry, that we find for a differential equation allows us to reduce the differential equation once. This property from this theorem allows us to reduce the differential equation twice. And the details of that lies in the fact that if you take the definition of a first integral, remember we said that di dx is equal to 0 on the differential equation. We're dealing with ordinary differential equation, i.e. technically this I will be equal to some constant, right? Which implies that that first integral, you would construct minus k is equal to 0, and if you took the vector field, and of course you'll have to prolong it, and operate it on I minus k, this we know, when x1 operates on I, you get 0. When x1 operates on a constant, you get 0 is equal to 0. So you got x1 on xi minus k is 0 on the differential equation. And this is in fact the result that allows, remember, this is a first order differential equation. If you started off with a second order differential equation, y double dash, etc., I is a function of y dash, so this is first order. And here you have x is a symmetry of this first order differential equation, which means you can reduce this first order differential equation by the same x that you would use to reduce the second order differential equation. So this leads us to the notion of double reduction of differential equations. So this is loosely one of the applications of knowing Noether symmetries as opposed to knowing Lie symmetries. A Noether symmetry is a Lie symmetry anyway. That's going to give you one reduction. And via this property here, you're going to get another reduction. So if you take a second order ODE and you reduce it twice, you'll get to a zero order, which is the solution of the differential equation.